A. Today I'm here to present and to discuss the topic of atomic absorption spectrophotometry that we learned for the past week. So this will be the objectives for today's lessons and presentation. We will learn the definition, components, discovery of FAAS, why FAAS, and when to use FAAS, and the importance of using this technique, the process, and the benefits. What is atomic absorption spectroscopy? So let us first discuss what is the meaning of this. So atomic absorption spectroscopy is the one that used as a analytical technique that studies how radiated energy and materials interact. We will learn the interaction between the two energy and materials. So matter absorbs energy, which will create some sort of change in its state. It is used to determine how much certain elements are in a sample. So what is atomic absorption spectrometry? The atomic absorption spectrometry is the one that detects elements in either liquid or solid samples through the application of characteristic wavelengths of electromagnetic radiation from a light source. We can measure the concentration by detecting the absorption of electromagnetic radiation by atoms rather than the molecules. We need to emphasize that this is atoms, not the molecules. Additional information for the atomic absorption spectrometry: the amount of light absorbed in proportional to the concentration. So ground state means relaxation, while the excited state is the one that makes the atom move faster, or they are moving fast. So the atomic absorption spectrometry, the excited atom then returns to the ground state, emitting light of the same energy as it absorbed. It means that as electrons return to their original energy state, such as being excited, or from excited state to back to the ground state, they will emit energy in the form of light. This will be the components of FAAS. First is the light source, where we will get the source of light that we will be using to the FAS. And the second is the flame, or the flame that we'll be using, and the nebulizer, where we place the sample solution such as liquid and solid. Monochromator, this will be the one responsible for collecting the information, and the detector will be the one who will get the results of the atoms being isolated. Light source. So a hollow cathode lamp. This type of lamp is the one that is commonly used and contains a hollow cathode made of the element being analyzed. This includes an anode electrode. So gaseous ions bombard the cathode, which ejects metal ions. The cathode concentrates most of these emitted ions into a beam that passes through a quartz window. So nebulizer. Deliver a fine spray of the sample containing your metallic ion into your flame or your cylinder. A nebulizer is a device that introduces a liquid sample into the AAS or FAAS and uses the combustion flame to atomize and introduce the sample into the light path. So flame and burner. This is the one that is the sample cell of the instruments. So this is also an atomizer. Dissociate the solution into its neutral and individual atoms. Detector. The photon detector is the one that is responsible for counting light in photons. Photons are the elementary particle, the tiniest possible particle of light in an electromagnetic field, the one that is being gathered to this technique. So monochromator or monochromator, the light absorbed by the sample is in pulses. Thus, the light it emits is also in pulses. So its main function is to isolate the wavelength of interest from the broad spectrum of wavelengths emanating from the lamp, from the hollow lamp. So we will be discussing the discovery of FAAS or the AAS. So first in 1802 was the atomic absorption spectrometry was the first discovered because through the observation and describing the dark lines in the sun spectrum by the English scientist William Hyde Wollaston, the one who first discovered the atomic absorption spectrometry. In 1817, the German physicist Joseph von Fraunhofer, I don't know the pronunciation, but he's the one who carefully mapped out the spectral absorption lines, which are now named after. This is the benefits of this technique. So it is a relatively simple process drawing on well-documented protocols. It allows us for high throughput of samples. It is inexpensive in comparison to the another analytical techniques. It supports a broad range of industries and sectors including environmental, chemical, petrochemical, food and drink, and pharmaceutical. So thank you for listening. I hope that you learned something from this presentation. Thank you.